The big thing that gave us trouble was figuring out who was n and who was n sub 0. Well, this number is always the bigger. This is always bigger because it's the original, and things start decaying from there. So on the graph that we've been making, this point here, the vertical intercept, is n sub 0 or a sub 0. Another way to put this is the number of nuclei at the point of maximum nuclei. You could also call this n max and a max. That might make it easier to solve problems if we just call this n max and a max. And the number always decays from there. And then we use the same algebraic trick of taking the log of both sides. And you can take either the natural or the regular log here, but we took the natural log. You have to be careful with the negative signs. Make sense? Like I said, that's a popular type of problem. By the way, lambda times half-life is the natural log of 2. And if you have this in your cheat sheet, then it doesn't matter whether they tell you lambda or the half-life, because you can always figure out the other one. So if they tell you the half-life, you could use this equation to find lambda, and then if you felt like it, you could use the lambda equation. Or if they give you the lambda, you could use this to find the half-life, and then you could use the half-life equation. Since you'll get a cheat sheet for the test, I guess you can just write all these equations down. By the way, let's figure out what lambda is for iodine 131. We just saw that the half-life here was 8.04 days. So you just did the natural log of 2 divided by 8.04. If you go back in your notes, this is the lambda I gave you for the previous problem. This is how I figured it out. The table gave me this is the half-life, but I wanted to do a problem with lambda, so I figured out the lambda here. So this was the lambda we did for the previous problem. How would we interpret this number? How do we interpret this decay constant?
It's 8.6% is decaying per day.
Per day, because we're working with days here. That's right. So this is really percent decay per day. This means each day about 8.6% are decaying, and this means it takes about 8 days for half of them to decay. Two ways of giving the same information. Okay, so here I guess we've got the big 5 equations for radioactive decay. There's 2 equations that when you're working with lambda, you can work with either n or a, and they have the same form. And there's 2 equations for when you're working with a half-life. Again, you can work with either n or a, and they have the same form. And which one do you use? Well, if they give you the half-life, you would use the half-life equation. Or if they give you lambda, you would use the lambda equation. Except that actually, if you know either lambda or the half-life, it's easy to figure out the other one using this equation. So now we have lots of options when we're wanting to solve these equations. We can do it more than one way. So I would put these 5 equations together in one place in the cheat sheet for the radioactive decay problem. So you're pretty sure to have to use these. Let's another problem. Let's do this one. Sounds good.
is equal to 7.4% of the original activity.
That's good.
So it's 0.074.
That's exactly right. We have to start by writing that type of equation that relates A and the original activity. The new activity is down to 7.4% of the original activity when the organism died. Good. So it's good to put that in our diagram. It's hard to draw this to scale because we should be right around here. We're only at 7% of where we started. We should be very far down here, only at around 7% of where we started.
This equation becomes 7.4. And the AOs cancel out.
That's right.
And then you do the L on both sides. Oh yeah, and the half-life. Charcoal.
Looks like you're missing a detail in the problem. What did they tell you more specifically about what's decaying?
Oh, carbon. Carbon 14.
That's right. So not everything in the charcoal is decaying. So we know that charcoal as a whole is not that radioactive. It's only the carbon 14 that's
So
decaying.
then it's 5,730 years.
Right. So by looking it up in the table, we know that the half-life is 5,730 years from our table of half-lives.
The L in 0.074 is equal to negative 2.60. And that's equal to negative t over 5,730 ln of 2.
Good.
T divided by ln of 2. To get negative 3.76 is equal to negative t over 5,730.
Good.
And then you get negative t equal to negative 21523.78. So positive t is equal to 21,524.
That's right. That's probably a lot more accurate than we're justified in being. We probably have fewer significant digits in this, but just to round off, this is
Years.
approximately about the right answer. Yeah, and the answer is in years. That was good. Well, this is again a very practical application. As you might have heard, this is the way archaeologists figure out how old things are with carbon-14 dating. So this is the famous carbon-14 dating. They know how much carbon-14 was originally in the organism when it died, and then when they can see how much is still left, and then they can figure out, it's good that you built this graph here. One thing you might have done is said that this is specifically the time we're trying to figure out, this time here. And then they can just do this math to figure out how much time it took for the original level of carbon-14 radioactivity to fall to the level that it's at right now. So this is a clever trick that archaeologists can use for thinking about time. Why did we focus on the half-lives? Because the table gave us the half-lives. Although if you wanted to, you could have figured out lambda and then used the lambda equation. The only thing that gave you trouble was finding the right substance. So the part of the charcoal that was important here was the carbon-14. Then you took the natural logs, and then this algebra seemed to give you much trouble. Okay, it looks like we made some good progress on that. Like I said, You'll probably see one or two problems about that on the test. These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks.